As always, let me know if there are any questions. Unmute yourself if you need to. Type it in the chat if you don't want to interrupt the audio. And then you've sent those questions to me, but now that we're going back, we're starting class normally, just make sure you set your chat to everyone again instead of just me so that everybody else can see your questions as we're going about. Yeah? Question number 1, which of the following statements is true about a closed system? This question is easy. This has been put in here to make sure you don't revise all of the little things. At the very beginning of module 5, we distinguished between an open system as well as a closed system. One thing I'll let you know also before we keep on going, because this is revision, I'll talk about things as if you're remembering it again and we're not teaching it for the first time. If you need me to stop because you're like, oh, hold on, I just realized I don't know this anymore, let me know so that we can talk about it properly. Yeah, I might direct you to the lesson recordings or we might go through it here depending on how much we need to cover. First inquiry question in the module 5 folder, one of the first things you learned when you started year 12 is the difference between an open system and a closed system. By definition, an open system can transfer energy as well as matter with the surroundings, whereas a closed system can only transfer energy between the system and the surroundings. There's no mass. If you get a short answer question on this and it's not a multiple choice question, then there are certain ways that you can phrase your response to make it sound better. If you feel like you're pretty good in your trials and you got a pretty good mark and you're sort of aiming for that very close to 100 or even 100 mark. Yeah. When we talk about energy transfer or mass transfer, we're talking about transfer across the system surrounding barrier. So you can either say, oh, it transfers energy and it transfers mass, or you can talk about it as a noun and you can refer to energy transfer and mass transfer across the system surrounding barrier. So there's a different sound when you say, oh, open systems can transfer energy and mass across between the system and the surroundings, and it sounds different if you say in an open system, energy transfer and mass transfer across the system surrounding barrier are both possible. It sounds different. This kind of stuff doesn't affect your marks in the grand scheme of things. It affects your mark if you're competing for state ranks and things like that in a state exam. Keep that in mind. When we talk about system surrounding barrier, what that means is that if you're looking at it in terms of the system, sometimes energy gets lost, sometimes energy gets gained, and that's when you start talking about endothermic and exothermic reactions. What I want to emphasize is there's a system, this is the surrounding. This entire thing, though, that encompasses the system as well as the surroundings is what we call our universe. Okay, so what I want you to keep in mind is when we talk about energy getting transferred, it means that it went from one place to another place. Do not talk about energy being lost or destroyed or quote unquote gained, because that implies that it went somewhere that it cannot be found again, or it came from somewhere that it wasn't in the first place. So you want to say energy moved away from the system or energy moved towards it, but you don't want to say it got lost or it got produced, because energy doesn't do that. Mass also doesn't do that. And that's because if energy or mass is sometimes in the surroundings and sometimes it's in the system, sometimes it's in the surroundings, regardless of where you put it, it's still inside this box in which the overall thing is called the universe. You don't want to refer to energy or mass as being lost or gained or made or produced or destroyed, because that goes against 2 of the laws of conservation that you learned in Module 2 of Year 11 and Module 4 of Year 11. In Module 2, you learn the law of conservation of mass. Mass cannot be created or destroyed. And in Module 4, you learn the law of conservation of energy. Energy cannot be created or destroyed. So lesson here, if you do get a short answer question about this, watch out for the way you word your response. Energy and mass are transferred. It is not created. It is not lost. If you get an exam question in the HSC that's worded a little bit funny and it asks you about the movement of energy or the movement of mass, then this is where this kind of content might come in. You might be wondering if this is still relevant. Enthalpy and entropy get referred to in the Module 5 syllabus. That's talk of energy. That's talk of law of conservation of mass. So it is possible that NESA words a question in a way that is about year 12 content, but does require you to recall a little bit of this year 11 stuff. Can I get a thumbs up? Does this make sense? When you're not learning anything new here, I'm just emphasizing the way you want to talk about something. Yeah? Okay. So the answer to this question itself is really straightforward. Energy but not matter is exchanged with the surroundings. That's it. Okay. You might get like a calorimetry question for module 7 or even module 6 that's like, what happened to the energy? It got transferred, but then the question might be like, did it get lost? Did it get gained? If the question does not say, if the question says, was energy gained or lost by the system, then you can say yes or no. If the question is, was energy gained or lost in general, that tends to mean, did it go away? Did it come from somewhere? Which is no. The answer to that, if they don't specify in the system, then the answer is no. Energy wasn't lost, energy wasn't gained. Because if they don't define a perspective, then they're talking about it in terms of the whole universe. The other thing I will tell you here is they might define a perspective, but they might not say the system. Be careful and watch out for if they define the perspective as these surroundings, yeah? Because in the very beginning of module 5, and when you learn it in year 11 as well, you're used to defining endothermic and exothermic reactions as exothermic reactions release energy into the surroundings, endothermic reactions absorb energy from the surroundings. So endothermic reactions, the energy goes up. Just watch out though, because if they talk about it from the surrounding perspective, an endothermic reaction decreases the energy in the surroundings. It increases the energy in the system. And then exothermic reactions, it releases energy. So in the system, it goes down, but in the surroundings, it goes up. So watch out for what perspective they define in the exam. Can I get a thumbs up? Does that make sense as well? Exothermic and endothermic reactions, when you talk about releasing and absorbing energy, you always do that from the perspective of the system. That just tends to be the way you do it. Watch out for if they ever define a situation in a perspective that you're not used to. Not just for endothermic, exothermic stuff, any other questions that you do. Yeah. For example, module 6 titrations, they might ask you about pH in the conical flask, or they might ask you about pH in the burette. Okay. Question, does pH in the burette ever change? No. Okay. pH in the conical flask changes because you're mixing the acid and the base. pH in the burette never changes because it's always an acid or it's always a base in the burette. So watch out for if NESA gives you a question that seems like you're used to it, but makes you look at it a different way, because that's how they get over the whole memorizing content kind of stuff. Question number 2, what is the equilibrium expression for the following equation? Equilibrium expression is concentration of products over concentration of reactants to the power of any coefficients that there are, excluding pure solids and pure liquids. What we mean by pure solids and pure liquids is it's the only liquid in there and it's not dissolved in anything else. Watch out for if you see two liquids being mixed together or two liquids coexisting in the reaction. One example of that is ethanol and water. Ethanol dissolves in water. You can also think of it as water dissolving in ethanol because they're both solvents, in which case you can actually define a concentration for ethanol in the water or a concentration of water within the ethanol. Anytime you can mix two liquids together, you can define a concentration. The reason we don't normally include pure solids and pure liquids is because there is no concentration to define. It kind of makes up the whole thing. If you want to see a question where water is actually included in the equilibrium expression, then it'll be one of the topic tests, one of these. I don't know if it was one of the ones that I set for you, but it was one of the topic tests. I think you might have done that test. So go back to have a look at it if you want to. In this case, the solid is a pure solid, so it doesn't get included. So you have Ca2 plus, OH minus, and the OH minus has a coefficient of 2. So your answer is going to be D. Any questions? Please feel free to interrupt me or type it in the chat or anything that comes to mind as we're going. Question 3. The equilibrium constant for a reaction is given. What is the equilibrium constant for the following reaction? K1 has an equilibrium expression of AC2 squared over A2 and C4. You want to compare the equation where a K is given to the equation where a K is not given and see what you have to do to manipulate it. In the first equation, the AC2 is on the right, but over here, the AC2 is on the left. So when you're comparing equations, you want to look at a few things. You want to look at position, left or right. And number 2, you want to look at coefficients if it's the same. Or number 3, you want to look at any missing chemicals that indicate that you might have to add equations together. In this case, because they've only given you one equation with one K value, you don't have to worry about missing equations or adding equations together because there's only one that can turn into another. We have done questions where there are 3, 4 equations given, and you have to add them all up to get the final thing. Go have a look at the previous lesson recordings if you want to revise that. In this case, there aren't multiple equations, so I don't have to worry about this third point. I only have to look at this. AC2 is on the right. I want an AC2 on the left, so I'm going to flip my equation. When I flip my equation, I reciprocate my fraction. This is the manipulation that happens to the K value when you're changing the equation. So then 2AC squared, 2AC2 turns into A2 plus 4C. The original was 4.8. This is going to be 1 on 4.8. And then you look at your coefficients. The coefficient of AC2 starts off as 2 and then it goes into 1. You multiply your coefficients to get it to the same. So if you have a 2 and you're trying to go to a 1, what do I times by? Times by a 0.5 or times by a half. When I times my coefficient by a constant, the K is raised to the power of the constant. So if I'm timesing by a half, that means I raise this whole thing to the power of a half. 1 on 4.8 to the power of a half. What do I get for the answer, please? 0.456, which is D. Thank you. Okay, if you want more revision on this one, please go and have a look at the lesson recording. Question 4, which of the following reversible reactions at equilibrium would not be affected by volume change at constant temperature? Volume changes and pressure changes go hand in hand when there's constant temperature. This is, you don't explicitly learn this in year 12 anymore, but if you want to mention it in a short answer question, that would be really nice. If you get asked about Le Chatelier's principle, at constant temperature, volume and pressure are inversely proportional. Who remembers the scientist from module 2 that said this? Boyle, yes. Boyle's law. Okay. If you would like to quote Boyle's law in your Le Chatelier's principle questions, feel free. The equation, if you're relating 2 points together, P1 V1 is equal to P2 V2. This isn't really useful for Le Chatelier's principle, though. This was more useful for year 11. For year 12, it's probably better to just use this equation. P is equal to K on V. This equation is probably better if you want to include it in Le Chatelier's principle questions. Just tell a marker according to Boyle's law where P is equal to K on V, where K is a constant. Otherwise, they might think that K is some kind of variable, in which case that goes against your definition. So if you want to bring this in to elevate your response, just make sure you mention this as well. Pressure is caused by gases. Boyle's law is a gas law. So volume changes only leads to pressure changes if you can change the amount of gas in the system. If you let your reaction proceed and the amount of gases at the start and the amount of gases at the end is the same, then it makes no difference. So when it asks you for which one wouldn't be affected by a volume change, that's the one where the moles of gas on the left and the moles of gas on the right are the same. To count moles in chemistry, you're just adding up the coefficients. In every single chemical here is a gas, so I can add up all of the coefficients. Just watch out for if you get a question with a solid in there, or a liquid in there, you don't add the coefficient of those solids and those liquids. In this case, I don't have to take that precaution. In A, how many gases on the left and on the right? 3 to 2 in B, 1 to 2 in C, 1 to 2, and in D, 2 to 2. Good. So you're adding up these invisible coefficients out the front. If there's no coefficient, then it's a number 1. D is the only one where it's the same. So that's going to be your answer. Exam question, multiple choice question wise, if you're struggling with figuring out an answer, or let's say you didn't know the theory to get to the correct answer in the first place, then you have a few options. Hopefully you're able to just extrapolate as much information as you can out of it. If you see a question that's really, really different in terms of the information that you get and it stands out, that will usually be your answer. But it requires you to know at least a little bit, yeah? So even if you didn't know about volume changes and Boyle's law, hopefully with enough revision, the fact that it talked about volume changes sort of triggered something in your head to just count up the number of moles of gases, even if you didn't really know why. And hopefully from that, when you got these numbers, even though you don't know which one's the correct answer, you might be able to identify that, hey, in A, B, and C, the number of gases change, and in D, that's the only one where it stays the same. In a multiple choice question, out of the 4 options, there can only be one that's right. That's the answer. So there has to be something different about it, which means if you're really, really struggling with a question, and you don't really know where to get to the answer, your last resort is to figure out which one is most different from the other three, which are similar. And that's sort of like your fingers crossed moment where it might be the answer. Can I get a thumbs up, guys? Does that make sense? That's your last resort for if you're trying to figure out a multiple choice question in particular. This technique doesn't work for short answers, multiple choice only. Yeah? Any questions? Type it in the chat. Question 5, typically, so some of you guys asked for KSP questions. This is the start. Typically, the molar solubility X of an ionic compound in pure water and its KSP are related by a simple formula. Which formula is not expected for KSP for an ionic compound? This question looks really vague, and it will sound awful if you haven't done any molar solubility calculations at all. This isn't a question where a random person who hasn't studied chemistry can come in, yeah? When you look at these 4 options, hopefully you recall that it looks like the expressions for when you're done setting up an ice table for an ionic compound, and then you put the expressions involving X into the equilibrium expression and see what you get out of it. So this question is basically asking you, what ratio of ions in an ionic compound would not lead to one of this? For example, if you get an ionic compound that is AgCl, and you do Ag plus Cl minus, and you do ICE 0, 0, plus X, X, and X, then when you put it into KSP, your expression is X squared. This question is basically asking you, when you set up your ice table, based on these changes, based on the ratios, which one of these just doesn't happen? So you can trial and error, or you can do it based on memory. Which one just doesn't show up? So if I did CaCl2, this is Ca2 plus, this is Cl minus, and you would get plus X plus 2X, and then the KSP for this would be X and 2X squared, and then you'd get X, 4X squared, 4x3. So this 4x3 is possible. The question's asking you for which one's not possible, so it's not A. You change it one at a time. Notice how I went 1-to-1 ratio, and then I went 1-to-2 ratio. You can't do a 2-to-2 ratio, because a 2-to-2 ratio is the same thing as a 1-to-1 ratio. So you just keep on going with 1-to-3, and that might be something like silver phosphate, for example. So Ag3PO4. And then that would give you Ag plus PO4 3 minus plus 3x plus x. 3x to the 3 with an x is 27x3 with an x is 27x4. So C is not possible. So if you see how many times it changes based on this pattern alone, anytime it goes up by an x, so from x3 to x4, the number also changes. Like it doesn't go 4x3 and then 4x4. It goes x3 and x4, and then the number changes from 4 to 27, just based on how the maths works. So even if you didn't want to trial and error it further, just to confirm the 81x5, based on this pattern here, you can be pretty confident that 4x4 is not possible. Can I get a thumbs up? Does that make sense? In case you didn't want to get to the 81x5, you can see pretty clearly that 4x4 just isn't going to happen. If you want to test it though, it's not too difficult to do. If you get something, I don't even know where you'd get a x5 power from. Something with a 4 minus. Let's just make it up. If you get something that's like A plus B 4 minus, and then this will be 4. This would be plus 4x, this will be plus x. 4x to the 4, and then x. And then 4 to the 4 is probably going to give you an 81. Just give me a thumbs up in the chat if when you put in the calculator, that's what you get. 4x to the 4 with an x should be the 81x5. 256. So 4 to the 4 is 256x to the 5. Which means your answer is D. So 4x4 where might you get a 4x4 ratio? 1 to 1, 1 to 2, 1 to 3, 1 to... Oh! So you can do a 1 to 1, you can do a 1 to 2, you can do a 1 to 3, you can do a 2 to 3 ratio. Yeah. You know how I told you earlier, you can do 1 to 1 and then just change one of the ratios at a time, go to a 1 to 2. And then I told you that you can't do 2 to 3. And then I told you can't do 2 to 2 because 2 to 2 is the same thing as 1 to 1. So then we kept changing the second number 1 to 3. When you get to 1 to 3, though, you can do a 2 to 3 ratio. If you do a 2 to 3 ratio, you can also get an x to the 5. So let's do a 2 to 3 ratio and then see if that gets you an 81, because we need to figure out what the answer is. Is it one of these two? So 2 to 3, that's something like calcium phosphate. So 3Ca2 plus, 2PO4, 3 minus. This is going to be plus 3x. This is going to be plus 2x. So then you'll get 3x to the 3 and a 2x to the 2. 3 to the 3 is a 27. 2 to the 2 is a 4. That's x to 5. What do you get when you do 27 by 4? 108? x5. 5, you can do 1 plus 4. You can do 2 plus 3 with a 4. You can do 2 plus 2, 1 plus 4, 1 plus 3. If you do, let's say you do, if it's a 2 to 2 ratio, then you'll get, when you do your ICE table, then you'll get a plus 2x and a plus 2x, which is 2x squared with a 2x squared, which is 4x squared times a 4x squared, which is a 16x4. So you will never get a formula where it's a 4x4, and you also won't get a formula where it's an 81x4. So in a case like this, your answer would be both B and D. That has happened before in a multiple choice question for the HSC. They've been pretty good at getting rid of it recently, but just watch out for in the exam. If you've exhausted all of your options and you feel like one of them's correct, but the other one's also correct, then it is possible that the question's been written slightly incorrectly and there are two answers. Can I get a thumbs up, guys? Is that okay with us? We haven't seen it in a while. I can pull it up for you if you want proof of it. It's very early on, but there has been one HSC question where they had two answers. So in this case, when you test out your options for what gets you an x4 power and an x5 power, there's no way you get a 4 and there's no way you get an 81. So both B and D are not possible. Question 6. If equal volumes of BaCl2 and NaF solutions are mixed, which of the following combinations will not produce a precipitate? The KSP of BaF2 is 1.7 times 10 to the minus 7. This one requires you to genuinely do remember a bit of your theory. Something forms a precipitate if QSP is greater than KSP. If QSP is equal to KSP, and it's only a 1-mark question in the exam where it's asking you for precipitate forms, then your answer is, if you get QSP is equal to KSP on the dot, then the answer is no, a precipitate does not form. Watch out for how many marks the question is, though, and the way the question is worded. If the question asks, does a precipitate form, 1 mark, that's a yes or no answer. If the question asks, what conclusions can you draw from your result, and it's like a 2-mark question, then your answer is still, it doesn't form a precipitate, but you want to get a bit of extra detail in with the 2nd mark. Because QSP is equal to KSP, you only need to add 1 more drop of whichever ion to get QSP to tip over to be greater than KSP, at which point a precipitate will form. So in the exam, gauge how many marks the question is and how much you have to write. If it's equal on the dot, the system's at equilibrium, it won't form a precipitate, but you are on the tipping edge of forming a precipitate. If you add 1 more drop, QSP will become greater than KSP and you will form the precipitate. So your job here is to sub in the different concentrations and see which one gets you a number greater than this. So QSP is the Ba2 plus and the F minus concentration squared. They haven't given you the concentrations of the Ba2 plus in particular, and they haven't given you the concentrations of the F minus in particular. They've given you BaCl2, in which there is Ba, and they've given you NaF, in which there is F. In this case, it's fine because the coefficient of the Ba is 1-to-1 with the entire molecule, and the coefficient of the F is 1-to-1 with the entire molecule. Watch out in exam questions though. If this was, let's say this was CaF2, what would you have to do to the concentration of CaF2 to get the F minus concentration to sub in to your equilibrium expression? You'd have to times it by 2, yeah. So if you had 0.02 molar CaF2, there's 2 fluorines in every molecule. So if you wanted just the fluorine concentration, that would actually be 0.04 molar F minus. So watch out for in the exam. You have to do that, but in this case, it's fine. So this multiple choice question is straightforward. All I have to do is sub it in each time. So for A, what you're doing is, based on this, you're doing 0.004 times 0.02 squared. For B, you're doing 0.010 times 0.015 squared. And for C, you're doing 0.015 times 0.01 squared. And for D, you're doing 0.02 times 0.002 squared. So pop this in your calculator. Let me know what you get for QSP, and we can figure out which one has QSP greater than KSP. I don't know, James. You have to give me the numbers. I don't have my answers with me when I do this with you guys. Because if I do, then that means I'm just giving the answers and then you guys don't use the calculator. 1.6 times 10 to the minus 6, which is greater than 1.7 times 10 to the minus 7. So your answer is A. Can I get a thumbs up? Everybody else got the same thing? Yeah. Thanks, Samra. Thanks, Siobhan. Thanks, Nora. Good. Thanks, Cody. All right. Your answer is A. If Q is greater than K, is that a precipitate? If Q is greater than K, then a precipitate will form. The question's asking you which one doesn't form a precipitate. What's your answer to B? So with A, a precipitate will form. The question is asking you which one will not produce a precipitate. (2.25 times 10 to the minus 6, which is still greater than 10 to the minus 7. So that one forms a precipitate. 1.5 times 10 to the minus 6. Feel free to give me your answer for D as well, but we can see from A, B, and C that they're all greater than 10 to the minus 7. So by the process of elimination, your answer has to be D. That's the one that should be less than 1.7. Yeah. So 8 times 10 to the minus 8 is less than 1.7 times 10 to the minus 7. So that will not form a precipitate, which is what the question is asking you for. Okay. When you go to do your studies, and also with the kind of answers that you guys gave me, please reflect in your own time whether or not, like how your answers came about. If you told me you don't need to revise module 5, for example, because you've revised absolutely everything, then that's fine. I'll let that go. But just watch out for if the reason you say you don't need to revise something is because the questions in the trial on that module happen to be easier, or you didn't get as much on that module. So please just reflect when you go to do your studies. I would recommend getting a blank syllabus Word document and typing everything you know out, just to make sure that you actually do know everything on a module that you claim to know everything about, and it's not just because you haven't been exposed to it recently. Certain questions, now that you finish your trials, you can stop doing the trial papers and go into the HSC papers. When you go to start doing the HSC past papers instead, watch out for the questions that you see a lot of and the questions that you see less of, because those are the ones that might end up popping up in your year. So I'll let you know from my own observations for module 5, certain syllabus dot points you want to watch out for really carefully. Enthalpy and entropy calculations we've never seen yet. The question that we're about to do here, we've never seen yet. Keep in mind that the new HSC has only been out for, this will be the 5th year it's being tested. So there's still quite a few things we haven't seen. Enthalpy and entropy we haven't seen. We also barely saw a common ion effect question. It showed up in a multiple choice question in the 2020 HSC, but we haven't seen much of a calculation question on it yet. So watch out for that one also. This is for module 5. We'll give you the list for module 6 and module 7 as we go. So these ones, watch out for just in case it shows up. Question 7, explain why the combustion of ethanol is an irreversible reaction. We need to know the syllabus and the way it's worded, because there will be some questions where the answer just isn't obvious to you based on the words of the question. Question number 7 is one of them. It requires you to know what was under this syllabus dot point in the syllabus. And what's under this section of the syllabus is the idea of enthalpy and the idea of entropy. From year 11, you actually briefly talked about equilibrium. If you get, who remembers, for a spontaneous reaction, what does Gibbs free energy need to be? Negative, yeah. If you have a delta G less than 0, then the reaction's spontaneous, which is what we said in year 11. And then if you have a delta G greater than 0, then it's going to be non-spontaneous. And then we said very briefly in year 11 that if you get to the middle spot where delta G is equal to 0, that's when it's at equilibrium. Okay, so if it's at equilibrium, it's reversible, it goes back and forth. So if the question's asking you for why is it irreversible, then this is not the case you're explaining one of these cases. So your job is to pretty much link enthalpy and entropy together to figure out if combustion is spontaneous or if combustion is non-spontaneous. You've done combustion reactions enough though. Are we arguing G less than 0 or are we arguing G greater than 0 for a combustion reaction? Non-spontaneous? Your combustion reactions happen all the time when you did it in class though. When you're turning on your car, when you put your magnesium strip into the Bunsen burner to get that bright white light, it happened really easily. So that means it's spontaneous. So the combustion reactions that you've ever done in class, they happen really quickly. They're spontaneous. So for combustion, we're actually arguing delta G less than 0. So in summary, if you get a question that's asking you to explain why something is reversible, you only have one case. Delta G is equal to 0. If you get a question that's asking you to explain if it's irreversible, you have to consider which of the two cases you're going to talk about. Are you going to talk about this reaction being really spontaneous, or are you going to talk about this reaction being non-spontaneous? That requires you to recall what you know about the reaction. Combustion reactions are really spontaneous, so we're gonna go this route. Can I get a thumbs up, guys? Does that make sense? If it's reversible, you only have one case, the third one. If it's irreversible, you have to pick which one of the two cases you're going to talk about. Less than 0 or greater than 0. Yeah? We'll talk about combustion first. Combustion is specified in the syllabus, which is why I'm talking to you as if you know it. And then we'll talk about what happens if they give you a reaction you don't know. Yeah. Combustion reactions, exothermic or endothermic? Exo. What I'm going to do, because they've specified ethanol here, I'm going to set up my equation really nicely. I'm going to give them the equation at the start, and I'm going to be like, this is what the combustion of ethanol looks like. And then I might even make it a thermodynamic equation by putting the delta H next to it. And then my first paragraph will be enthalpy and my second paragraph will be entropy. So my formal answer to question 7 will be, I'll have to write it in dot points, but the equation for the combustion of ethanol, and then you'll skip a line, you'll give them the equation, C2H5OH, liquid plus O2G turns into CO2G plus H2O. And then to make my answer even better, because I'm aiming for that band 6, because I might even be fighting for a state rank, I'm not just going to say combustion, I'm going to say what kind of combustion? Just to elevate my response. Good. So in my answer, I'm going to say the equation for the complete combustion. These little things add up when you're competing for the top ranks. Liquid. And then the fact that I've put liquid here, what else might I say? For the complete combustion at, let's say, 25 degrees Celsius, or you can say at standard conditions, because I've specified liquid. If you decide to do bracket G, then you can say, oh, at whatever temperature you like, because it normally operates at maybe like 100 degrees Celsius, if you want to mention it that way. I balance my equation, 2 here, 3 here, and a 7 on 2 here. And then heat, yes, no. So I'm going to do delta H less than 0. I don't actually know the number for the enthalpy of combustion of ethanol. This one's not one worth memorizing because when you did your combustion experiment in module 7 for alcohols, you did it for different alcohols, so you don't remember it. If you ever get a neutralization question though, and you would like to put the enthalpy in, I can give you that one. Delta H for neutralization, if it's a strong acid and a strong base, is minus 57.6 kilojoules per mole. This one is not supposed to change. This is the theoretical enthalpy for neutralization, yeah? So for combustion, I can't give you the answer. It changes depending on what you're combusting. But if you want to talk about it in neutralization, because you do enthalpy of neutralization in module 6, if you're fighting for those really top marks, feel free to include this number in. So I'll talk about this. Where's the O2? Would the O2 coefficient be 3? Yes. So there's 2 by 2 here, which is 4, with a 3, which is 7 oxygens on the right, but I have 1 oxygen here. So if I do 3 by 2 gives me 6, plus 1 gives me 7. Thanks, Savan. If I'm going too fast, please let me know. Let me know when you want to slow down with this kind of revision, yeah? Regarding enthalpy, if you have, I don't know if the state of H2O is going to be gas or liquid. That's why I specified this at 25 degrees Celsius at the start. If you get an exam question that specifies the temperature for you, then do it according to that. If it's below 100 degrees Celsius, give them L. If they're asking you above 100 degrees Celsius, give them G. I just put L here because I chose to, because the question doesn't specify, but that's why I specified my own temperature at 25 degrees Celsius. If you've got a lot of time in the exam and you want to make each of your answers perfect, then I would go ahead and actually define what enthalpy is. Before you go into your explanation. Not crucial though, unless you're really fighting for those top marks. If anyone is interested, enthalpy is the total heat content in a system. Would the combustion happen above water boiling point, therefore it would be a gas? Yeah, it would. So in real life, the water that gets produced would be steam. It's just that I happen to define the equation in this answer at 25 degrees Celsius. That's all. But yes, if it happened in real life, it would be gas. It would be a vapor. Spontaneous reactions move in the direction that enthalpy and entropy like to go in. Enthalpy likes to go in a decreasing energy reaction because it's more stable. So enthalpy is the total heat content in a system. Combustion reactions are always exothermic. Delta H is less than 0, which is favorable. And then I start my entropy paragraph. Who remembers the definition for entropy? Yes, entropy is a measure of the disorder in a system. Ethanol is a really bad example for this. You start off on the left-hand side, you get 1 mole of liquid with 3 mole of gas to 2 moles of gas and 3 mole of liquid. Ideally, you get more moles of gas because in that case, it's really easy to argue that entropy has increased. We know combustion reactions are spontaneous, so it would have been really nice if our equation was set out in a way that the moles of gas increased. I could cheat though. I could change my equation so that I get more moles of gas. How could I do that? What would I change in my equation? Because at the moment I have 2 moles of gas and 3 moles of liquid, which doesn't look good. Yeah. I can still argue that entropy increases. There are ways to do that, but I don't really want to. So what I can do is at the start, I defined it at 25 degrees Celsius and I put water as a liquid. To cheat my way in a little bit, I might actually just change this to gas. And then I'll say the equation for the complete combustion of ethanol above 100 degrees Celsius is this. So then how many moles? So then what do I have on the right-hand side now? On the left, 1 mole of liquid, 3 moles of gas. On the right, I now have what do I have on the right now? When I change from L to G. 5 moles of gas total. Yeah. So now I call this cheating. I'm sorry. If you wanted to keep it at 25 degrees Celsius and keep it as H2O, there is a way to reason to the answer and say that entropy is increasing. But it's a 4-mark question. Not really worth it. There are probably more important questions to do in your upcoming exams. So I'm gonna cheat. I'm gonna change it. So moles of gas increased, therefore increased disorder. If you are fighting for those top marks, instead of talking about disorder, you can talk about number of microstates that the system arranges itself into. This is the more sophisticated definition of entropy. And then because of that, delta S is greater than 0. And then enthalpy and entropy aren't enough to talk about spontaneity. Whether or not a reaction is spontaneous is, like you guys told me earlier, delta G is less than 0. So this doesn't finish me off for my answer. I'm going to skip a line again in this kind of question, and then I'm going to say, because delta H is less than 0 and delta S is greater than 0, delta G is equal to delta H minus T delta S is less than 0 at all temperatures. We don't reason our way to this anymore in year 12. If you would like to, as an exercise, feel free. Anytime you have a negative delta H and a positive delta S, whichever way you calculate it, whatever number you sub in for T will always give you a negative delta G. If you would like me to send you the lesson recording from year 11 to prove this, let me know. But otherwise, use it as an exercise on your own. Therefore, combustion reactions are highly spontaneous. And I'm not going to stop there because the question didn't ask me to say it's spontaneous. The question asked me to say why it's irreversible. Spontaneity is just a step to getting to the talk about reversibility. So I don't stop my sentence here. I don't full stop here. I say, therefore, combustion reactions are highly spontaneous in the forward direction. If it really likes one direction, it really doesn't like the other direction. So I'm going to say it's really spontaneous in the forward direction and non-spontaneous in the reverse, therefore irreversible. And this is probably the most elevated form of this response that I've given you so far. If you recall, we've done this answer before, but it didn't look as much like this as it did when we first covered it. Last year. We first covered this last year, guys. Module 5 was 2023. Okay. Can I get a thumbs up? Does this make sense? Does it look okay with us? Do we have any questions? Okay. Can I get a thumbs up, guys? Does this look good? Do we have any questions? Okay. Well done. All right. Take a quick break for me. 7:50, we will get back into it. Let me know if there's anything you want to talk about, anything that you thought about during class, anything you don't want to tell me earlier. But otherwise, 7:50, we'll get back and we'll keep on going with the questions. Feel free to give me feedback as we're going. If we're going and you realize that there's something you don't care about or there's something you really do care about, let me know. I asked the questions at the start, but you can continue to answer them throughout the next 7 weeks. Okay, if you would like to draft an answer to this response and send it through, feel free. Can I just give me a thumbs up? You're able to hear me all okay? Okay, good. Thank you. All right. We used we used to have a different version of this for our last year's year 12s. And the reason we're not reusing that document is because I moved all of those challenge questions from last year's HSC revision into your question book. So anytime you saw those like really, really, really hard questions in like the module 5, in all of the question books actually, that's where they came from. The document last year was called challenge questions, and then I moved it all into this year's question book. The thing is, though, you might look back and you're like, I don't know what questions she's talking about because they don't seem that hard to you anymore, which is good. It means you're elevating, and the questions continue to get harder each year, but you guys continue to get better, so you can't tell anyway. That's something nice to reflect on. Question 8, the energy profile diagrams of two reactions, A and B, are shown. Which reaction is more likely to be reversible? Justify your answer with reference to this information provided. So the reason I put this question in is because it's worded differently, but it applies the same content that you know. So these are, like, question A is the kind of question you expect to see in the HSC that looks kind of weird, but you should be able to get your way to the answer somehow. If you saw there are only 4 past HSC papers for the new syllabus from 2020 to 2023. Do the papers before 2020 though, because there are still questions that are relevant. But I want to emphasize doing at least 2020 to 2023. Don't just do the latest one. The 2023 one, lots of people have the opinion that it's the easiest one so far. So don't let last year's paper let you get your guard down. You can bring your guard down after you finish all of your exams. Yeah? Not for now, keep them up. So, question 8. You learned the content right before the break. We went through it. So we're just applying it now to this graph. Before the break, though, we went through both enthalpy as well as entropy. This question doesn't give you any indication of entropy. So it's a 3-mark question, which means you don't have to consider as many concepts because question 7 was 4 marks. So we really only need to talk about enthalpy here. Now, A is the bolded line. So this is A. Did energy get absorbed or did energy get released by the system? Absorbed, because the delta H slightly went up. So this is delta H greater than 0. So what kind of reaction is reaction A? Endo. James. Oh, wait, no, who said that? Yeah, James, what happened? Delta H is greater than 0. A is endo. And for B, which is the dotted line, it's here down to about here. So energy released or absorbed? I drew the arrow down this time. This is released. So then delta H is less than 0, which is endo or exo? Exo. And then based on what we talked about before the break, which one is more favorable, endo or exo? Exo. Are you just giving me both options now to see which one I focus on? Exo. Thanks. Thanks, guys. So exo is more favorable. Gauge how many marks the question is in the exam. I doubt that this will come up, but it is very possible. It might be a bigger mark question. If you get anxious about if you're going to get enough marks or not, and you want to know how much detail you can add, without being repetitive, because you don't want to be repetitive to get the extra mark. If you don't have anything new to say, just don't say it. But if it's if it goes up to 5 or 6 marks, I pray that it won't for this kind of question. It's just not worth it. And you feel like you need a bit of extra detail to explain why EXO is favorable. EXO releases energy. Less energy is more stable. This is something you learn in year 11, module 1. This is one of the, I would argue this is one of the first principles in chemistry. Things happen to try to get to a state of lower energy. The first time you were exposed to this was when you learned about flame tests and electrons jumping back to the ground state. We like less energy. Less energy is more stable. So feel free to bring that in if you judge that you need to based on the amount of marks in the question. So EXO is more favorable. So notice how the question doesn't say which reaction is reversible. This question asks which reaction is more likely to be reversible. Because for you to judge reversibility, you need to judge both. You need to judge both enthalpy as well as entropy. So exothermic reactions are more favorable. But here's the thing though. What did we link exothermic reactions to in question 7? Did we link it to the fact that it's favorable? Did we link that to it being spontaneous, or did we link that to it being non-spontaneous? Combustion before was exo, and we linked it to it being spontaneous. And then here's the issue. In question 7, when we linked it to spontaneity, did we link it to reversible or irreversible? Irreversible, yeah? So in this case, we're actually thinking about it slightly differently. Because we don't have both the enthalpy and the entropy to talk about it, then you take a slightly different approach. So exothermic, more favorable, more likely to be spontaneous. More likely to be spontaneous means it really, really likes that direction, which means it's irreversible based on what we talked about before. Because with the previous question right before the break, we said combustion of ethanol, exothermic, favors that direction. If it favors that direction, it doesn't favor the other direction. That makes it irreversible. We need something that doesn't mind going in either directions. Question 7 was asking irreversible. Question 8 is asking reversible. They're asking you for the opposite things. So exo means favorable, means spontaneous, usually means irreversible. So then if the question's asking about which one's reversible, I'm actually inclined to go the endothermic and reaction A route, not reaction B. Can I get a thumbs up? Does that make sense? I don't want to confuse anyone. 7 and 8 are asking you for opposite things, yeah? 7 asked you for irreversible, so we talked about exo. Question 8 is asking you for reversible. So we're probably gonna go the endo route. Now, for those of you that aren't convinced, there is another way to think about it. What do you normally use to judge if a reaction is going to proceed? That was thank you, James. I was gonna say that's a vague question, but I want to see if anyone can get it. Activation energy, yeah. We summarize it as endo and exo because that's what you get after talking about activation energy. Thinking about things always in terms of first principles is really time consuming, but sometimes I go back to it to prove to you what we talk about. Activation energy. to be really, really sure of our answer, we can talk about activation energy. The reverse and forward reactions, activation energy is near equal. Yeah, exactly. So activation, the lower it is, the easier it is to go in that direction. The issue happens when the activation energy for one side of the reaction is really low and the other side is really high, which means only one side likes to go and the other side doesn't really like to go. If you get a reaction where the activation energy doesn't change that much, it's kind of willing to go in either direction. Okay. Where do we draw activation energy on an energy profile diagram? For enthalpy, we go reactants to products. Where is the line for activation energy? And stationary point and for enthalpy, it's reactants and products. For activation energy, it's between which 2 points? Initial and peak. Good. For enthalpy, we went reactants to products. For activation energy, you go the start up until the peak. So for reaction A, this one here, this is the activation energy of the forward reaction. And then guys, if you're trying to look for the activation energy of the reverse reaction, reactants to products, products to reactants. So the activation energy of the reverse is here up until the top. Okay. That's for reaction A. Yeah. So let's take that out so that we can compare it later. This is for reaction A. And then this is reaction B. Activation energy of the forward reaction. And then reverse reaction. This is reaction B. Which reaction has the bigger gap? Which reaction has the bigger difference in activation energy between the forward and the reverse? Exo, the B reaction. So because there's a bigger gap in activation energy, does that mean it likes to go both ways or it's harder to go both ways? Is it easier or harder to go both ways? Harder. Which way is it easier to go for, the forward or the reverse? The forward. Whenever activation energy is low, it's easier to go that way. So for exo, it's way easier to go forward than it is for reverse. For endo, reaction A, the gap, the difference in activation energy isn't that different. Notice how this is the gap. That's the gap. Whereas for this one, this is the gap. So that proves our point in terms of first principles. Earlier, we were talking about it in terms of spontaneous and Gibbs free energy because it's easier to do it that way. It doesn't take as long. This proof took a little bit longer, but it proves your point a lot better. So which reaction is more likely to be reversible? Which reaction goes both ways a little bit easier? Your answer is reaction A. Justify your answer. The difference in activation energy between the forward and reverse reactions is smaller. So it's easier to proceed in both directions. Okay. Can I get a thumbs up, guys? Does that make sense? Good. I know this is revision, But because we're building on the stuff that you've already learned, it does seem like we're talking about stuff in a way that's harder. Maybe that's just my perception and you're kind of like, this is fine, miss. But let me know if you do have any questions. Yeah. The reason first principles is always a really good way to do it because it gets your point across really well. It's a little bit harder to do though, because first principles is the kind of stuff you learn in year 11 module 1. You won't get deducted marks if you talk about it differently as long as you get the answer right. Please don't get starry-eyed by thinking about it in terms of first principles though, because you might just be wasting your time in the exam. It takes a lot longer to do. And depending on the marks and depending on the question, it just doesn't get you that much value. Yeah. So use this carefully. The reason I used it here is because there was enough information to do it here. In question 7, you don't know the activation energy. They haven't given you any values. They haven't given you an energy profile diagram to look at. In this case, because they've given you an energy profile diagram, you can physically see the difference in the activation energy. That's why going about it this way was good. This is called an energy profile diagram. If you would like to explicitly refer to that in the question, in your answer to the question, that would elevate your response a lot. Any questions, please let me know. Question 10, I'll leave for you to do. Question 11 is a standard Le Chatelier's principle question. I'll leave for you to do that as well. I'm going to skip past the graphing questions for now. I want to show you question 17. For those of you that want more challenging calculation exam-based questions. Question 17, calculate the value of the equilibrium constant for the following equation, given that the Ka1 of H2C2O4. Does anyone know, does anyone remember H2C2O4? What's the name? Ka1 of it is 6.5 times 10 to the minus 2. Ka2 of it is 6.1 times 10 to the minus 5. Yes, oxalic acid. Thank you, Noyo. And the Kw of water is 1.0 times 10 to the minus 14. All right. Can you give me a thumbs up? Does anyone remember a similar question to this when we did it in module 5? This doesn't give you brownie points or anything, but out of curiosity. We don't remember. That's good. I will show you for the first time. Please get your pens and pencils ready. After we do this question, I'll direct you to the question that I'm talking about. I think I pushed you a little too hard when we did this kind of question when you first learned module 5, and this wasn't even revision. This was just right after you finished your basic equilibrium constant calculations. I brought in a question like this, but in my defense, introducing you to it early means that everything else you see you think is a little bit easier. So let's say you get faced with a question like this in the exam and you're like, I have absolutely no idea what to do. What did we always say? When we were doing module 6 together with those challenge questions, what did we say about questions that we don't know where to begin? What did I tell you guys to do? Work backwards? Yes, let's start there. There was something else that I told you. If you remember it, let me know. But let's try that first. Work backwards. Calculate the value of the equilibrium constant. For an equilibrium constant, you need an equilibrium. Equation, they've given me the equation. Alongside the equation, I need an expression. Yes, so if I were to work backwards, equilibrium constant with the equation, with the expression, and then, guys, when you write out the equilibrium expression is just a function of what? Is it a function of moles? Is it a function of mass? What kind of values do you sub into the equilibrium expression? It's a function of concentration. So then, now, if we were to really go backwards, then I would take this all the way to concentration is moles on volume, and then moles is mass on molar mass. Working backwards doesn't work that well for this question because you can't go back very far. You stop going backwards once you've got the information you needed. The issue is, though, you kind of stop here because with this question, based on the numbers they've given you, you don't have concentration, you don't have moles, you don't have volume, and you don't have mass on molar mass. Okay, so one technique was to work backwards. There was something else that I told you that wasn't really a technique for when you just absolutely don't know what to do. Which was, rather than working backwards, what I was basically doing there, we were working backwards, but we were labeling what we could and getting as much information that we could from the question. And then you try to piece it together. Give me a thumbs up if you remember that. I told you that if you don't know where to go, you brainstorm everything you can and see how you can link the information together. Yeah. Let me know if you remember that. Working backwards only works if they've given you enough information to piece it together to work forwards again. Here, the three numbers that they've given you, it's all equilibrium constants. Kind of can't piece that together. Yeah. So my next best option is to write down everything I can and see how it works. Okay. What we did though wasn't in vain, because you guys told me equilibrium constant gives you an equation, and when you get an equation, you get an expression. So like I won't keep on working backwards. I won't go to moles, I won't go to mass. I'm going to stop here, but I'm going to apply that to each of these. Because I expanded it for the word equilibrium expression. Why can't I do that for these actual equilibrium constants? For the unknown equation, I can only get the equilibrium expression. So for this one, let's say K is equal to C2O42 minus. Do I include the H2O? No, I don't. I have H2C2O4 OH minus squared. That's the only thing I can do for that. But for Ka1, Ka2, and Kw, I do know. Does anyone know what this 1 and 2 means? Because you know Ka and you know Kb. What does it mean when there's a number next to the Ka though? No, they're both K. So they're both K. I'm asking about the little number. It's a different number of proton donations. Good. We don't see it very often because we're used to working with acids that are monoprotic, which means it only releases one proton, so you only write one equation for it anyway. But if you remember when we did conjugate acid bases, we wrote the equation for getting rid of one proton, and then if it still had a proton left over, we wrote another equation. Yeah. So the fact that there's the fact that it stops at Ka2, what does that tell you about oxalic acid? Monoprotic, diprotic, triprotic, quadprotic, I don't know, diprotic. Di means two. The fact that you can write two dissociation equations for it means that it can release two protons. So Ka1 is going to be when it releases the first proton. I'll do it over here. H2C2O4. When I write dissociation equations, it's always acid and or base plus water. Thank you. Get rid of the first proton first. When we did module 6 at the very start, I told you to get rid of one proton at a time. If you see H2SO4, get rid of one proton at a time. We do the same thing here. So HC2O4 minus. And then they've given you the number. So this is Ka1 is HC2O4 minus H3O plus over H2C2O4. is 6.5 times 10 to the minus 2. And then you do the same thing for Ka2. For Ka2, do I start here? I'll say number 1, or do I start here, number 2? What do I put in this side? When I go to write my second dissociation, do I write this chemical or do I write this chemical? Yes, I write the second chemical. When you go to write successive dissociation equations, you don't start at the first molecule. You keep going with whatever you end up with. Yeah. So it dissociates once, it turns into HC2O4 minus. That's what I put at the start of my second equation. So this now goes over here and it ends up being HC2O4 minus. And then I just put in my second, I take out my second proton. So this now becomes C2O4 2 minus aqueous plus H3O plus. That's 6.1 times 10 to the minus 5. And then they tell you the kW of water. Does anyone recall from module 2, from module 6, what the equation is for kW? Yeah, but the chemical equation. The chemical equation that you use to write the equilibrium expression. Yeah, so H3O plus OH minus turns into water, but the other way around. So it's the ionization of water, not the if you have the water on the right, that means you're synthesizing water, you're making it. KW is when you're ionizing water, when you're turning into the ion. So just the reverse of what Curdy told us, H2O liquid turns into H plus. There's two ways of doing this, yeah? Turns into H plus plus OH minus. The only issue is, though, if I have a H plus, it doesn't relate to anything. Like there's no H plus in this equation that I'm trying to get to, and there's no H plus here, and there's no H plus here. But H plus is closely related to H3O plus. So this actually isn't the equation for KW. This is the equation for the ionization of water, but the equation for KW in particular is not when you're breaking apart one water, it's when you're reacting two waters together, one's an acid and one's a base. So what ends up happening here is this is the proper equation for KW. If anyone's confused and you want me to expand it for you, let's say this one acts as an acid and it goes over here, it ends up with OH minus and H3O plus. That's where the two waters comes from. Yeah. So this is the equation for the KW. And then, so you might not remember this, but this should look familiar. This one here. Yeah. So all those times in module 6 where we were doing this equation, this is where it came from. And that's 1.0 times 10 to the minus 14. KW is 1.0 times 10 to the minus 14. What temperature is this reaction happening at? 25. KW is only equal to 1.0 times 10 to the minus 14 at 25 degrees Celsius. So if you get a part B to this question that's like, what assumption did you make about this reaction? It's all happening at 25 degrees Celsius. Okay. All right. I've written out everything that I can. Now I want to see if I can link it together somehow. Okay, so you've got the equilibrium expression, you've got the equilibrium equation, and then hopefully you can see that this equation here that you're trying to get to, parts of it show up in different parts here. Yeah, so let's see if you can figure it out for me. In the desired equation, this one here, let me label this 1, 2, and 3 for the 3 equations. In the desired equation, you have H2C2O4. Which equation do you see that in? 1, 2, or 3? H2C2O4. Which equation do you see that in? Of the 3 that we wrote together in equation 1. So H2C2O4 shows up here. What about OH minus? Where does that show up? Shows up in the third one. What about C2O4 2 minus? In the second. Oh, different color. And then the H2O shows up everywhere. So after expanding all of the information out and noticing that different parts of your desired equation show up in the different equations that you wrote, what do you think we have to do? Can I just use one equation for my working out, or does it look like I have to combine my equations together? Combine them. So now I'm going to ask you this. Is combining equilibrium equations new to you, or you've done this before? Have you done this before? Combining equations and equilibrium constants together? Yes. Did you do it today? Sort of? Kinda. You didn't, the question we did earlier didn't combine them together, but you did slightly manipulate it. It was this one here. So, and also, this is a revision lesson. So the answer kind of has to be yes, you've done it before, because otherwise I'd be lying to you and this isn't revision. So that wasn't done to mock you. I want to show you, I just want to let you know that any question that you see moving forward will never be a question that you can't do. Yeah, I really, really believe that. Any question you see moving forward, it'll never be a question that you can't ever do. You have everything you need to do, unless you haven't been studying the whole year, but none of you are like that. So I'm adding these equations together to get the equation that I want to have. Okay, so you told me that, so we'll start off one by one. The H2C2O4 is seen in the first equation. We want to check position left or right, and we want to check coefficients. So this is what we want H2C2O4 to look like. This is what H2C2O4 currently looks like. Do I want to do anything to the first equation? Or is the H2C2O4 exactly how it's meant to be? Yeah, I don't want to do anything to it. H2C2O4 is on the left. I want it on the left. It's got one coefficient. I want one coefficient. So this one, I'm going to keep exactly the same. That one's a tick. And then the OH minus only shows up here. Do I need to manipulate equation 3? Yes. What do I have to do? Two things. I have to reverse it and have to times it by 2. Good. Because OH minus in equation 3 is on the right. I want it on the left, and it doesn't even have the same coefficient. So I'm going to change this. Be careful when you're keeping track of your changes. Do it one at a time. OH minus aqueous plus H3O plus aqueous turns into 2H2OL. What did we say happens to the K value when we flip the equation? Reciprocal. Good. So instead of 1 times 10 to the minus 14, I get, well, guys, 1 times 10 to the minus 14 is just 1 on 10 to the 14. So this here, if I flip it, it's just going to be, this is just going to be 10 to the 14. Can I get a thumbs up? Is everyone following the maths so far? I don't want anyone to get confused by the numbers. If you get confused by the chemistry concepts. Yeah, not the numbers. 1 times 10 to the minus 14 in fraction form is just this. If anyone's confused, please let me know. So then when I reciprocate it, I just bring the 10 to the 14 up the top. If anyone's confused by the maths, pop this in your calculator, and then you'll see that it gets you this when you put it in scientific notation form. That'll be your proof. And then James said we've reversed it now, but James said we also have to times it by 2. So I times it by 2, 2OH minus aqueous plus H3O plus, plus 2H3O plus turns into 4H2O. What did we say happens to the K value when you times the constant? Exponent becomes raised to the power. This becomes 10 to the 28. Okay, so I've manipulated equation 3 now. Take a screenshot if you need to. I don't want you to get confused. So what I'm going to do is get rid of the original equation we had and just have the manipulated one now. I'll move this up if anyone wants it. So I won't delete it just yet, but I'm going to bring this one now. So this is now in the format that we want. 10 to the 28. And then the last one we have to check is equation 2. Equation 2, we had the C2O42 minus. Do I want to do anything to equation 2? No, it's on the right. It's got a 1 coefficient. So I'm going to keep it the same. And then now that I've got all the 3 equations in the format that I want them in, I can add them together. And then we'll talk about what happens to the equilibrium constant after, but I just want to make sure that when I do add them together, I actually do end up with this equation. Yeah, because I'm not gonna do anything to the numbers until I have my desired equation. So let's bring this one a little bit closer and then talk about what happens when you add them. So this is the same. Okay, are there anything on opposite sides of the equation that you can cancel out? Because when I add equations together, I want to simplify it. I simplify things if they exist on opposite sides. Hydronium. There's a H3O plus here on the right. There's a H3O plus here on the right. So that's 2 H3O pluses on the right. And then I get 2 H3O plus on the left. Okay. James also said water. How many waters do I have in total on the left from all 3 equations? 2. How many waters do I have on the right? 4. So I can only cancel 2 out. I'm going to cancel these 2 on the left, and I'm going to cancel 2 from the right, so I'll end up with 2. What else can I cancel out? HC. Good. Everything else I can't cancel out. It stays where it is. What do I have left over on the left? I have this here. I have H2C2O4 aqueous. And then I have this. And that's it on the left. Everything else I canceled out. And then on the right, I have this. And then I have this. Okay. Does that match the equation that the question is asking me to get? Because if it doesn't match, I'm not supposed to multiply all the numbers. Yes, it does. So when I added all three equations together, remember, because you only adjust whatever equations you need, I needed all three equations. That gives me the equation that I want. Now, if I adjust all three equations, I have to adjust all three numbers. Who remembers what happens to the k value when you add equations together? This one we didn't revise with the previous question. Who remembers? Starting with an M. Or the T, depending on how you talk about the operation. You multiply, yes. When you add equations together, you multiply the equilibrium constants. So the K of this is going to be 6.5 times 10 to the minus 2 times 6.1 times 10 to the minus 5 times, you take the manipulated ones. The first two equations you didn't manipulate, times 10 to the 28. So what is the K of this equation? Can I confirm you guys got 3.965 times 10 to the 22? Yep. Thanks, Evan. How many sig figs do I want to round off to? 2. So my final answer is 4.0 times 10 to the 22 to 2 sig figs. Any units? No. Equilibrium constant is unit length. Okay. This is, are you able to see by inspection that the desired K? Yeah, you could do it as well. You could do it that way as well, Savan. You could, yeah. Mhm. All right, this is equilibrium expression on steroids. If you would like to see another question like this, if you would like to jot it down, question for extra practice, question 114 from your module 5 question book. I think there's a video answer on it as well if you want to watch a video. Question 1, yeah, there is a video. So feel free to attempt it first now that you've done a question like this because it's fun, I dare say. This is one of the questions where you kind of don't want to look at the typed answer for, so feel free to watch the answer to question 114 when you're ready. Okay, next lesson we'll focus a little bit more on your ICE table calculations and your KSP calculations. I'm aware some of you have identified that, and we also need to talk about the common iron effect in a little bit more detail. Okay? All right.